Hi, we are now in the data layer. Let's learn about data ingestion. Before your AI can answer questions about your documents, that data has to get in somewhere. This video covers how to build the pipeline that makes that happen. A pipeline, by the way, is just a sequence of steps where the output of one step feeds directly into the next, like an assembly line for data. So, what is it? Data ingestion means bringing raw data into your system in a usable form. The word ingestion means taking something in, like eating. Your AI system is eating your documents. It takes raw content from PDF files, databases, web pages, APIs, cleans and transforms it, splits it into small searchable pieces, and loads it into something called a vector database. We will explain what a vector database is in a moment. Think of it like a restaurant prep kitchen. Raw ingredients arrive from suppliers. The prep team cleans and chops everything before service starts. By the time cooking begins, all ingredients are ready to use immediately. Your documents are the ingredients. A vector database is the prep station. If you have built ETL pipelines before, you already understand the concept. ETL stands for extract, transform, load, and that is exactly what data ingestion does. The only difference is the destination. Instead of loading into a data warehouse, you load into a vector database. The tools you will use are LangChain, which is a Python framework for building AI applications. It provides document loaders, which are ready-made connectors for reading different file types. You will also use Chroma, which is a vector database that stores your document chunks locally on your machine. Next, workflow. First, raw sources. Your PDF files, databases, APIs, or files in cloud storage like Amazon S3. S3 stands for Simple Storage Service and is Amazon's file storage system. Second, extract. A document loader reads the raw content and converts it into Python objects your code can work with. Third, transform. You clean the text, removing duplicate sections, fixing broken formatting, stripping irrelevant boilerplate like page numbers and headers. Fourth, chunk. This is where you split long documents into smaller pieces, typically around 500 characters each. A chunk is just a short fragment of your original document. The word chunk here means exactly what it sounds like, a piece of something larger. You also set a chunk overlap of around 50 characters. Overlap means the end of one chunk and the start of the next chunk share the same 50 characters. This prevents a sentence from being cut in half across two chunks. Fifth, load. Each chunk gets converted to a vector and stored in the database. A vector is a list of numbers. We explain this in the next slide. The three boxes at the bottom break this into ETL. Extract loads the raw content, transform cleans it, and load stores the final embeddings. Next, let's see key concepts. 3 things to understand. First, document loaders. A loader is a connector that knows how to read one specific type of source. The PDF loader knows how to read PDF files. The web loader knows how to fetch and parse HTML pages. The SQL loader knows how to query a database. LangChain has over 50 of these built in, so you rarely need to write one yourself. Every loader returns the same document object format, which is just a Python object containing the text content and some metadata, like the source file name and page number. Second, chunking. You cannot feed a 200-page PDF to the AI all at once, because AI models have a context window, a limit on how much text they can read at one time. Think of it like short-term memory. Chunking solves this by splitting documents into small pieces that can be retrieved individually. The overlap prevents a sentence from being cut across two chunks and losing its meaning. Third, storage. Each chunk gets converted to a vector and stored in the database. If a sentence starts at the end of chunk 1 and finishes at the start of chunk 2, the overlap ensures both chunks contain the complete sentence. Third, embeddings and the vector store. An embedding is the process of converting text into a list of numbers. Those numbers are called a vector. The key insight is that text with similar meaning produces similar numbers. So when you search the vector store with a question, it finds the chunks whose numbers are most similar to your question's numbers. This is called similarity search, finding things that mean something similar, not just things that contain the same keywords. The vector store is just a database that is optimized for this kind of number comparison. Let's see project setup. Install the required packages. LangChain is the main framework. LangChain community contains the document loaders and the Chroma integration. ChromaDB is the actual vector database library. PyPDF is the PDF reading library. It is a separate install and easy to forget. Python.env loads your API keys from a .env file, which is a plain text file named .end that stores secret values like API keys outside of your code. If you want to use OpenAI embeddings, add your OpenAI API key to that .env file. If you want a completely free option with no API key at all, install Sentence Transformers instead. Sentence Transformers is a library that runs embedding models locally on your own machine. You will have two Python files. Ingest.py runs once to process and store your documents. Query.py runs whenever you want to test a search against the stored index. An index here means the stored collection of vectors, the same word used in database indexing. Put your PDF files in a folder called docs before running ingest. Next, ingest.py with OpenAI. This version uses OpenAI embeddings and requires an API key in your .env file. The code has 3 stages. First, it loops through every PDF file in the docs folder. The os.lister function lists all the files in a directory. A directory is just another word for a folder. For each PDF, it creates a PyPDF loader and calls the load method, which returns one document object per page. Second, it creates a recursive character text splitter. The word recursive here means the splitter tries to break text at natural boundaries. First, a double line breaks, then single line breaks, then spaces working from the most natural split point down to the least natural. You set a chunk size of 500 and an overlap of 50. Third, it creates an OpenAI embeddings object, which connects to OpenAI's embedding API. The Chroma.FromDocuments method takes all the chunks, sends them to OpenAI to get their vectors, and stores everything in the Chroma_DB folder. Persist directory means the location on disk where Chroma saves the database, so it survives between runs. Next, ingest.py with HuggingFace. HuggingFace is a company and open-source platform that hosts thousands of free AI models. The model we use here is called All-Mini-LM L6v2. Mini-LM stands for Mini Language Model. It is a small, fast, and accurate embedding model. L6 means it has 6 layers. V2 means version 2. This model downloads about 90 megabytes on its first run, and is then cached locally. Cached means saved to disk, so it does not need to download again. After the first run, it works completely offline. The only line that changes from the OpenAI version is the embeddings line. You replace OpenAI embeddings with HuggingFace embeddings and pass the model name. Every other line in the file stays identical. This is an important design principle. The rest of your pipeline does not care which embedding model you use, as long as you use the same one consistently. Next is query.py. After running ingest file, you need to verify it worked. QueryFile does this by loading the same Chroma database and running a test search. You load the vector store by pointing Chroma at the Chroma_DB folder and passing the same embedding function you used during ingestion. This is critical. If you use a different embedding model here than you used in ingest.py, the similarity search will return nonsense because the numbers will be in completely different scales. You call similarity search with your question and k equals 4. The k parameter controls how many results to return. K stands for the number of nearest neighbors in the mathematical sense, the 4 chunks whose vectors are numerically closest to your question's vector. The results show the source file name, the page number, and the first 200 characters of the chunk text. If the chunks look relevant to your question, the ingestion pipeline is working correctly. Next, other source types. The same pipeline works with any source type because all loaders return the same document format. The web-based loader takes a URL and uses a library called Beautiful Soup under the hood to parse the HTML. HTML stands for Hypertext Markup Language. It is the code that web pages are written in. Beautiful Soup strips out the HTML tags and returns the plain text content. The CSV loader reads comma-separated value files. CSV is a plain text format where each line is a row and values are separated by commas. The loader converts each row into a separate document. At the bottom, you can see all three sources combined into one list. You can mix any combination of source types into a single list and pass it through the same splitter and vector store. This works because the document format is a common interface, a shared structure that all loaders output and all downstream steps accept as input. Next, FastAPI endpoint. This slide shows how to accept document uploads over HTTP. The endpoint receives a file upload using FastAPI's upload file type. Upload file is a special FastAPI class that handles multi-part form data, which is the format browsers use when submitting file upload forms. The uploaded file is saved to a temporary location using Python's temp file module. Temporary here means the file is only needed for the duration of the ingestion. After the chunks are stored in Chroma, the temporary file is deleted using os.unlink. Unlink is the Unix term for deleting a file. The pipeline inside the endpoint is identical to ingest.py. Load, chunk, embed, store. The only difference is the source is an uploaded file instead of a folder. You can test this endpoint with curl using the capital F flag to attach a file. The @ symbol before the file path tells curl to read the file from disk and send it as an upload. Let's see common errors. If PyPDF is not found, install it separately. It is easy to forget since it is not bundled with LangChain. If similarity search returns empty results, your embedding models in ingest and query do not match. They must be the exact same model name and version. This is the most common mistake in this workflow. If you get an invalid dimension exception from Chroma, the cause is the same mismatched models. Dimension here means the length of the vector. Different models produce vectors of different lengths, and Chroma cannot compare vectors of different lengths. Delete the Chroma_db folder and rerun ingest with consistent embeddings. If the docs folder is not found, create it manually. Python will not create it for you. If OpenAI authentication fails, load.nev is missing from the top of your file. Without it, the API key from your .env file never gets loaded into the environment. The takeaways: data ingestion is ETL, extract, transform, load, the same pipeline pattern you already know as a backend developer. LangChain has over 50 document loaders. You almost never need to write a custom one. A chunk size of 500 characters with 50 characters of overlap is a reliable starting point for most document types. The embedding model must be identical in both ingest.py and query.py. This is the single most common source of broken results. Use HuggingFace All Mini LM L6 v2 for completely free local embeddings. No API key, no cost, works offline after the first download. Next up is RAG, which stands for Retrieval Augmented Generation. That is where you connect this vector store to a language model and start getting answers from your own documents.